Welcome to today's lecture. If you like playing games and solving puzzles, I believe you'll enjoy today's lesson. Today we'll address the I element and proof of DMAIC by exploring design of experiments. Although the lesson title may be a little bit foreboding and unsettling, once we get into the lesson, I think you'll actually find it to be kind of fun. Design of experiments has been around since the 1920s. As with many concepts, it took a while to become accepted. These days, many organizations use DOE to great benefit. We'll begin with an overview and discuss what a design and an experiment are. We'll review the history of DOE and discuss its nature. Then we'll identify the principles of sound experimental design. Then we'll work on three applications, one factor at a time, OFAT, full factorial, and fractional factorial DOE. Let's get started. Before we get too far in the lesson, let's take a bit of time to dissect the phrase design of experiments. We'll start with design. A design is a plan or an arrangement. It's something that we intend to do. So it's a purposeful, intentional activity that collects data about observations. The design piece of DOE is vital because it controls, within reason, the risk of incorrect decisions. And what about an experiment? In our context, it's not about using test tubes to blend two substances in a chemistry lab. It's a special type of statistical study in the sense that it involves collecting information so you can take action. This type of statistical study differs from what we discussed so far because what we study in DOE doesn't exist until we create it. Our experiments will focus on elementary units that we subject to different conditions and observe their reactions. Another interesting thing about our experiments is that they are comparative. Comparative experiments involve examining and contrasting properties of two or more populations. For example, a company may be interested in learning which method of injection molding will produce the more uniform parts. Also, a marketing manager may want to know what blend of promotional factors best reach potential customers. To find out, the manager uses test marketing, experiments, or she manipulates advertising, publicity, sales promotion, and point of purchase displays to determine the various levels of reactions. DOE provides a powerful way to achieve breakthroughs in improvements in product quality and process effectiveness. From a business perspective, this leads to increased market share, lower costs, and higher profits. I hope this sounds enticing. So why don't all companies use DOE? Sometimes it's a lack of awareness, but most of the time it's a fear of having to use statistics for a concept that may be too much to handle. It's my goal to demystify DOE so that everyone can use it successfully. A traditional experiment uses the simple idea of trial and error. Think about the last time you went fishing, assuming you have. You used worms and your best friend used a homemade lure made of feathers, reflective metal, and a few beads. You went home empty-handed while your friend caught so many fish that he invited the entire neighborhood over for a fish fry. Your next time out, the two of you decide to swap. You use the lure and your friend uses worms. This time, you have better success. You catch two fish, but your best friend again catches the limit. So much for trial and error for this experiment. From a purely scientific perspective, the trial and error method, where you change one variable at a time, has been a standard for many, many years. This is because if you change more than one variable at one time, how do you know which variable produces a change? While logically sound, this method is potentially misleading and becomes inefficient and costly as the number of variables increase. DOE is a systematic approach that considers many or even all variables at once. This is ideal for businesses that face budgetary restrictions and time constraints. So what is DOE really? It's a test or a series of tests that includes changes to input variables so that we can observe and identify changes in outputs. It's unusual for a single variable to explain an output measurement. It's more the case that a number of variables explain an outcome. This is the major purpose of DOE. If these words don't adequately define DOE, I think a picture to the right will. You may be wondering where DOE came from. Sir Ronald Fisher began using statistical methods for experimental design in Great Britain in the 1920s. His initial applications were in the biological and agricultural sciences. The first industrial use of DOE was in the British textile and woolen industry in the 1930s. Then in 1935, Fisher published the book, The Design of Experiments. After World War II, DOE was introduced in the United States and other parts of Europe as people began to discover Fisher's book. Since the quality movement in the 1970s and 1980s, DOE has been a staple of Six Sigma curriculums. Many universities require that engineering students receive formal DOE training as part of their undergraduate education. DOE is called a multivariate method. This is because, as our diagram illustrates, there are multiple inputs and multiple uncontrollable input factors. I don't want you to get the wrong idea that DOE is a free-for-all where everything happens at once in a haphazard way. It's useful to see what Fisher has to say about this topic. In considering the appropriateness of any proposed experimental design, it is always needful to forecast all possible results of the experiment and to have decided without ambiguity what interpretation shall be placed upon each of them. Fisher tells us that we need to define our expectations and how we should evaluate them once we finish each experiment. DOE not only gives us a significance test of the variable levels, but also gives us a model to predict the response. In a sense, DOE is similar to multiple regression analysis in that it addresses multiple independent variables. However, DOE goes one step further because it allows us to change variables to improve processes. Before we look at a couple of applications that illustrate the use of DOE, let's examine the principles of sound experimental design. First, list all objectives. Determine if the intent of your experiment is to improve a process or understand the contribution of different variables. Next, identify your assumptions. This is because the intent of your experiment is to identify all things that all people believe are the case. Next, define all known variables. In our exhibit, these are the X variables. List which variables you will change and which ones you will hold constant. Then determine the number of trials, and finally, list the sequence of variables. I think we have enough background information to work on a few applications. In the past, if you studied DOE, depending on what source you use, chances are you came across a method that was complex and filled with statistical calculations. Earlier, I told you I want to demystify DOE. Hopefully, we can do that with these applications. Suppose that we want to go into the medicated dog shampoo manufacturing business. We studied the pet products market and realized that pet owners spend big money on their spaniels, schnauzers, and all the rest. In a recent survey, dog owners cite dry, itchy skin as a major problem. It seems that no matter how often they bathe and powder their canines and give flea dips, their dogs just keep scratching. Since we have a few chemistry majors in our class, we decide to formulate a shampoo to remedy these pooch problems. Our first task is to set objectives. We determine that our shampoo will reduce dog scratching because of dry, itchy skin by 90% in the first 6 months of sale. Our assumption is that the dog owners will follow our directions and use the shampoo correctly. Next, we defined our known variables. 2 are common and 4 are more exotic. The common variables are water and sodium chloride, or NaCl, table salt, and the next 4 are exotic. Laureth sulfate, LS, cool tar solution, CTS, betamine, and glycerin. Our shampoo becomes a function of the following formula at the bottom of the slide. We know that in general, medicated dog shampoos use these ingredients or something similar, but we don't want to make just any dog shampoo. We want to make the best shampoo, so we decide to put our newfound DOE knowledge to use. In specific, we will manipulate some of these controllable variables to see how they affect the effectiveness of our shampoo. We know that our competitors previously tried the trial and error method to improve their shampoos with disastrous results. We heard that they tripled the amount of betamine, eliminated the glycerin, reduced the water by 50%, and used an inferior type of LS. Things were so bad that some of the dogs actually lost all their hair. Fifi, the poodle, was so embarrassed that she had to stay indoors for the better part of a year. The lesson learned for us is that if we aimlessly alter ingredients without a plan, we won't gain much knowledge about which factors improved or degraded our shampoo. Instead of the trial and error method, we decided to use the one factor at a time, or OFAT method. You just knew that it had to have an acronym. When we use OFAT, we change one factor but keep everything else the same. We also need to have at least 2 levels to evaluate each factor. We don't want to run before we walk, so we decided to change just 3 factors called A, B, and C that are most likely to make a difference in our shampoo formulation: LS, CTS, and NaCl. For LS, we decide to vary the contents by including either 0.10 or 0.15 milliliter per liter of shampoo. For CTS, we vary the material based on the supplier, buying from Paragon Incorporated or Bundy Supply. And for NaCl, we use either commercial grade or organic grade. Before we can begin our experiment, we need to run a baseline test. This helps us know how much we're improving or not when we begin our DOE. We start out with 0.10 of LS, buying CTS from Paragon, and using commercial grade NaCl. We try the shampoo on a representative sample of itchy dogs and find that it reduces scratching by 75%. And the good news is no dogs lost their fur. Now that we have this baseline, we decide to increase the level of LS to 0.15 while keeping everything else the same. It reduces scratching another 5% to 80%. So far, so good. Then we only change the supplier for CTS from Paragon to Bundy Supply. Things really skyrocketed. This formula reduced scratching by 88%. This was a 17% improvement over our baseline experiment. When we switched over to organic NaCl, there was absolutely no change to our baseline. The results were still 75%. So much for organic products. Let's stop and consider something for a moment. Does the lack of improvement because of switching to organic NaCl mean that this test was a failure? Not at all. It tells us that we should stick to the lower cost commercial NaCl. We would not have known this if we hadn't run the test. So far, we've used OFAT to improve our shampoo's performance from 75% to 88%. We haven't reached our objective of 90% yet, but we're making good progress. We don't want to forget what we've done, so we document our test results using a orthogonal design. This is a fancy name for a table with balanced columns. You can see that we have 4 columns and 4 rows. Let's take a look at our table, which I've reproduced on the slide. The minus signs reflects the level of LS, CTS, and NaCl we used in our baseline experiment. Our baseline levels are reflected in the first row since we all have minus signs. In row 2, we changed only factor A, LS. We know this because of the plus sign. In row 3, we changed factor B, CTS, and in row 4, we changed factor C, NaCl. Although we're doing well, I believe we can do better, but we have to make a change. We have to use the full factorial method. When we changed LS, CTS, and NaCl, we didn't look at all possible combinations. For example, what would we expect if we increased the levels of LS from 0.10 to 0.15 and switched from Paragon to Bundy at the same time? And to make things more interesting, what would happen if we also switched to organic salt when we made these other two changes? To test all possible combinations, we need to use a full factorial. A full factorial table expands upon our earlier orthogonal design, and I've reproduced it for you here on our page. We increased our rows from 3 to 8. This is because we're testing two levels and we have three factors, k. The full factorial formula for two levels is 2 to the k power or 2 to the third power, which is 8. We now have the capability of evaluating all combinations, and what we do is we fill in the results section of our full factorial table. There's one word for this table, wow. It looks like we've hit on a winning combination, 0.15 LS and CTS from Bundy. As we earlier stated, the changing of NaCl from commercial to organic grade doesn't make any difference. At a 93% level, we've exceeded our objective, which is the bottom row of this table. Now here's something to consider. What about the other three factors, water, betamine, and glycerin? We've not made any changes for these variables, but it may be possible to eliminate scratching completely. We can test them, but we'll need to run 64 tests, 2 to the 6th power. And if we wanted to check 3 levels for each of the 6 factors, we'll need 729 tests, 3 to the 6th power. As you can see, DOE can get expensive. For this reason, it's important that you plan your test out well in advance. Fortunately, there's a way to deal with all the possible combinations of factors. It's called the fractional factorial. Suppose that we did such a good job with the dog shampoo that we now have a chance to manufacture a dietary supplement for a client who is in the health products business. They'd like us to make a product that on average helps users gain 2 pounds per week. The supplement we come up with has 3 ingredients, X1, which is whey, factor A, X2, BCCA, factor B, and X3, biotin, factor C. For whey, we decide to vary the contents by changing the amounts from 3%, which is a minus for our baseline, to 4% plus of the total. For BCCA, we vary the material based on using bovine minus or poultry plus for our source. And for biotin, we use either reclaimed material minus or fresh material plus. Also, we have a fourth factor, D. It's the intersection of X1, X2, and X3 that is a secret proprietary ingredient. We could easily do a full factorial 2 to the 4th power, but the client is only willing to pay for 8 tests, not 16. We heard that the fractional factorial test can increase our DOE efficiency, so we decided to give it a try. We begin by placing A, B, and C in the first 3 column headings of a table. Next, we identify their possible interactions, A times B, A times C, and B times C, and then include the interaction of the 3, factor D, in the final column. In DOE terminology, this is known as confounding or aliasing. We use the basic principles of math to come up with signs. 3 negatives, minus times minus times minus, equals a negative. And 3 positives, positive times positive times positive, equals a positive, and so on. And in column 8, our very last column, we take a look at our full fractional factorial table. So far, so good. But suppose that when we show our table to our client, they want to know about the interaction between factor A, whey, and factor D, the interaction of A, B, and C. While it's not in this table, we can figure this out. We simply need to take the signs in each cell in factor's A column and multiply them by the signs in factor D's column. Here's what we come up with. In the first cell for column A times D, we have a plus sign because a minus times minus a minus is a plus. The third cell is negative because a minus sign times a plus sign is a minus, and so on. When you look at the pattern of the signs in the A times D column, you see something interesting. They are identical to the signs for column B times C. When we do the same for B times D, we find that the column is identical to A times C, and C times D is the same for A times B. If we evaluate the intersection of B times C, by definition, we also evaluate A times D. We can now update our fractional factorial table and also look at the various results when we run our test. And this is to the table on the right side. You can see that we hit the jackpot. We increased the weight to 4% of the total, used BCCA from poultry, and used fresh biotin as an average user weight gain was 2.25 pounds, which is shown on the bottom row. Interestingly, when you use 4% whey and poultry BCCA, but instead of fresh biotin used reclaimed material, the average weight gain was only 0.25 pounds. The catalyst was also different in the situation. I believe our client will be happy with our DOE results and we can commercialize this product. This concludes the lecture for today. I hope you found it interesting and that you're doing well.